In this video, we are going to talk about the second fundamental theorem of calculus. Sometimes it's called FTC2 or second FTC, and sometimes people actually call it first FTC and flip it with the other one. I'm calling it second FTC here. So what it says is this right here. Derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. There are some frequent responses that I see when people see this. What? Doesn't make any sense. Why is there an x here? Doesn't make any sense. And then what about the a? What about this a right here? This a here, it doesn't show up there. Why it doesn't matter? That doesn't make any sense. So hopefully with what I do here, I'll address all three of these. I'm going to start by asking you to do 4 warm-up anti-set problems. So I will put those up in a moment. Okay, these 4 problems that I'm about to show you are here to help you see all the whys, try to answer all these questions as we go through this. So calculate these 2 definite integrals. I'm doing that because this has a definite integral. Calculate this because I want you to remember your chain rule. And then calculate this because I want you to remember your U sub. So go ahead and hit pause, and the answers will pop up. Here they come. Okay, here we are. You should get 26 to 5x to the 4th cosine of x to the 5th. Some chain rule there. And then e to the x to the 5th. This chain rule works out perfectly for that to integrate to that plus a constant. Let me talk about this one. X cubed evaluated from 1 to 3. That gives me 27 minus 1, which is 26. Integral from 0 to pi of sine x dx. Well, that is negative. That's probably the error that will be most likely committed. Negative cosine of x evaluated from 0 to pi, which I leave the negative out front. And then I do cosine of pi minus cosine of 0. Cosine of pi is negative 1. Cosine of 0 is 1. Gives me this, which is 2. And then these two, I'm not going to go into an explanation of. Let me talk about these at first. What I want you to see is here, I'm integrating with respect to x, and my answer is a number. Say this was time, and I did the integral of from 1 to 3 of 3t squared dt. Well, I would get a number as well. What I'm trying to point out here with these 2 examples is that when I have a definite integral, the variable with which I am integrating with respect to, in this case x, does not show up in my answer. It gets integrated out. So if I come up here, that actually helps us see why this is at least not a t. You know, some people want to make this a t in this case, in this scenario right here. And look, I have a definite integral right here, and I'm doing it with respect to t. So whatever I do with that definite integral, there should be no t's in it, because when I do a definite integral, the variable that I'm integrating with respect to gets integrated out. And I think you'll see that as we go through some examples here. And we'll talk a little bit later about how these apply to what I want you to see as we move along. So I've copied the second FTC here, and now I'm going to do a simple problem that we could use the second FTC for. So example, we are going to do the derivative with respect to x of integral from 3 to x of cosine of t dt. Now, instead of doing this with the second FTC, I'm going to do it by hand. I'm going to do my actual integral, and then show you that it gives me the same thing that second FTC would give me. I think it'll also help you see some of the issues that I brought up above. So, first thing I'm going to do is calculate this integral. Ignore the derivative with respect to x for now. Well, that integral from 3 to x of cosine of t dt, well, cosine would integrate to sine of t. It is positive. And then I evaluate it from 3 to x. What would that look like? Sine of x minus sine of 3. So this right here is another way to write that. So what I'm being asked to do in this example is to find the derivative with respect to x of, oops, let me do a bracket. I'm going to replace this with that because they're the same thing. So that gives me sine of x minus sine of 3. Now, notice, first off, there are no t's in this, right? So I can't take the derivative with respect to time because there are no t's. So it should make sense that I'm doing a derivative with respect to something other than time. And notice, because of the x being in the bounds for this integral right here, I actually have x's in my solution. So it makes sense that I would take the derivative with respect to x of this thing. So now let's do this derivative. So the derivative of sine, well, that is cosine x. And then this is a spot where people sometimes write cosine of 3. But it's not. Remember, sine of 3, you could type that into your calculator and hit enter, and you will get a number. This is a number. It is not changing as x changes. So, therefore, the derivative of it is 0. So I get minus 0, which is just cosine of x. Now, I want to show you how we could get that same answer. So that's it. It kind of feels anticlimactic, I guess I should say. Like, all right, sure, that's our answer. And it becomes applicable in lots of scenarios. But that's my answer for this thing. So let me show you how I can get there using the second FTC. If we look at this right here, my f of t, so with second FTC. And remember, this is second FTC. So with the second FTC, f of t is equal to, what is it? It's cosine t. So this says that the derivative, oh, and then a is equal to 3. But notice there's no a here. And this just says the derivative with respect to x of this thing is just f of x. So if f of t is cosine t, f of x just says replace the t's with x's. So f of x is cosine x. Really, all I'm doing is taking this and plugging it in there and getting my solution out. So you should see that that's a lot faster than this, and there are actually lots of scenarios where I can't do this work in purple, and I have to use the second FTC in green. You will notice here, so one of the questions that I wrote, what about the A? Doesn't it matter? And I think, hopefully, you should see why the A does not matter. This could be a 3, a 5, a 10, a 200, as long as it is a constant, as long as it doesn't change when x changes, then what I said here, we're always going to get a number there. So that derivative is always going to be 0. So the A is inconsequential when I'm taking this derivative. So let's do a couple more. Let's do the derivative with respect to x of integral from 2 to x of e to the t squared minus 2t dt, close. So this one, I want you to try to use second FTC. Go ahead, hit pause, give it a shot, see if you can figure out what this is using the second FTC with that single step. Okay, this is just, here is f of t. It's that e to the t squared minus 2t. So what's f of x? It's just e to the, x squared minus 2x. And that's our answer. Hopefully you see that. We are going to quickly take a look at a FRQ and see how the second FTC plays a role there. So I'm going to pop it over. This is the 2016 AB FRQ number 3 from the College Board website. But look, g of x is the integral from 2 to x of f of t dt. So the first step is to find g prime. Well, what do we get when we do g prime? We get f prime of x. So hopefully this step right here, the first step of taking the derivative of this, makes sense to you. I'm going to go back to another example on the other thing. So we're going to now look at what happens with chain rule. And to do this, I'm going to give you the derivative with respect to x of the integral from 5 to x cubed of cosine of t dt. So this one, first off, you may say, well, what do we do with the x cubed versus the x? I'm just going to do this without the second FTC, the same way I did with our first example, so you can see what to do when we have something other than an x up in that upper bound. So let's just look at this for now, the integral from 5 to x cubed of cosine of t dt. So that evaluates the sine of t evaluated from, I'm going to write t equals 5 to t equals x cubed. So we know we're plugging in that t there. What's that give me? Sine of x cubed minus sine of 5. So again, this integral is the same as that right there. So we are trying to do the derivative with respect to x of sine of x cubed minus sine of 5. Notice again, when I do the derivative of the sine of 5, it goes away. So really all I have to do is do the derivative of this thing right here. Well, when I calculate that derivative, I use some chain rule. That gives me 3x squared times cosine of x cubed. Now what I want you to do is connect this to the second FTC, or to that FTC. How could we go directly from this line to that line and skip all this middle stuff? Notice the cosine gets my x cubed inside of it. So when I do this, this guy goes in there, but then notice I need to do this chain rule. I need to do the derivative of that x cubed. I get 3x squared out front. So whenever I do second FTC with something that is something other than just an x, I need to multiply by the chain rule out front. And in fact, when I do it with the x, I'm multiplying by the chain rule because the derivative of the x is just 1. But let's just rock into an example. So, whoops. All right, we are going to do the derivative with respect to x of the integral from 2 to x to the 5th of root t squared plus 1 dt. One thing I want you to notice with this one is that I've given you one for which we can't do it the way that I did it here. I gave you cosine of t. That's integratable. So we were able to integrate it and then plug it through and then take the derivative. It was longer, but we could do it. Here, root of t squared plus 1. At least given what I've taught you so far in this course, you don't know how to integrate that. It's more complicated than what we've gotten into. So I can't integrate it. Instead, I'm going to do the derivative using second FTC. So what do? Well, I need to do the chain rule piece out front. That would be 5x to the 4th. That's the same as this piece right here. And then what I need to do is go f of x to the 5th. So f of is squared plus 1. And what goes in there? This x to the 5th. So that actually simplifies to 5x to the 4th times the root of x to the 10th, not 7th, plus 1. And that's my answer, and I can get there super quickly using the second FTC. Let's see if you could do one more with chain rule. Let's do the derivative with respect to x of the integral from 0 to x squared plus x of ln of t plus 4 dt, close bracket. So the integral from of ln of t dt, and I want to do the derivative with respect to x. See if you can do that with the second FTC. Hit pause, see if you can do it yourself. Okay, we get chain rule out front. What's the derivative of that piece up top? It is 2x plus 1. I'm going to throw it in a set of parentheses. Now, what do? I plug this in for t. So what's that give me? ln of, and then the t gets replaced by x squared plus x, and then I need to have my plus 4. And that is how we do second FTC. Two places these typically show up, APFRQs, and in application problems, they'll be embedded into a problem. Peace.